I'm going to take you through a quick review of spectroscopy, atomic structure, bonding, intermolecular forces. This is just to remind you of the breadth of material that you need to know. For depth, you'll need to work a little more on your own. Spectroscopy, there probably will be a few questions on there. I'm not sure that you need as much depth probably as what is shown here. But again, it's simply the study of interaction of radiant energy and matter. And you can have all types of radiant energy with different wavelengths that are applied to the matter and all kinds of interactions that occur with that. So they're probably going to ask you some questions about PES and spectrophotometry and mass spec and so on. So just want to make sure you know what the general idea is and what the results of different energies will be. You've got infrared energy, and infrared, which is heat, is high enough to promote bond stretching. So you're going to stretch bonds back and forth. From stretching the bonds and relaxing them, you can actually find out the energy of the bonds. So this gives you information about the structure, multiple bonds, single bonds, and so on. UV and visible light energy is what your colorimetry and spectrophotometry are based on. This promotes electrons to higher orbitals and gives off different frequencies of light. Your short and UV light and X-rays will actually ionize molecules and break bonds. And this also gives you energy results that can relate to bonding. And then your microwave energy will rotate compounds and give you energy about rotation of bonds. So we're going to focus on absorption of visible light. If you absorb light photons, you're going to end up with increased energy. Your electrons will be promoted to an excited state and then fall back and give up light. Your basic idea is to remember that if you absorb wavelengths of light, all the other wavelengths will be transmitted, and this will give you the color. So it might be a good thing to know your light color wheel, to have an idea of absorbing. Red light will give you a green color, and so on. But I don't think you have to know much detail with that. The color is linked to the concentration, so the more light that is absorbed, the greater the concentration. So an example that I've seen before on the exam talks about hemoglobin appearing red because it absorbs blue and green light, and the degree of absorbance is proportional to the concentration of the hemoglobin. If you have several different substances that are absorbing at different wavelengths, it can be a little more difficult, but you want to pick what's called a lambda max, the wavelength at which the sample absorbs the most light. And most likely, that will be given to you with a graph. Now, you won't have the color behind it, but you can certainly see that the maximum wavelength absorbed here is yellow, so you're probably looking at a violet solution that you're picking, very similar to the lab you did when you had the crystal violet indicator that faded in your kinetics lab. The colorimeter, and they may say spectrophotometer, it's the same thing, an instrument that measures light of a specific wavelength that passes through a solution. Beer's law, absolutely the equations on the exam, you need to be able to apply it. The amount of light absorbed is directly proportional to the concentration, and by measuring the absorbance of light, you can determine that concentration. The Beer's law is on the formula sheet. Capital A is equal to ABC. A is the absorbance, C concentration, B path length, and A is the molar absorptivity. The molar absorptivity is specific for each substance. It is usually provided, it's a constant, it's usually given to you. I suppose they could ask you to solve for it by giving you all the other variables. The path length is the width of the cuvette, typically 1 centimeter, but it would be given to you. I can't imagine they would have you solve for it, so it will probably be provided. It might be something different than 1 centimeter, but it is a path length. light that has to travel through that distance. And then C is the molarity, or the concentration, and that's usually what you are solving for. We will work one free response on this. I only know of one that I've seen out there over the years, so we'll work that one. So you did a lab determining the nickel sulfate concentration. Obviously, the different concentrations would absorb different light, and you plot that standard curve and get the concentrations. You did that with the nickel sulfate, you did it with the crystal violet, and then most recently when you analyzed the purity of your aspirin. You make a standard curve. From the standard curve, you put the unknown in, you get its absorbance, and then read the concentration. Mass spec analyzes by using electromagnetic radiation. You're going to knock electrons off of your sample, turn them into charged particles, move them through the magnets, and hit the detector plate, and different masses are deflected differently. It's important to know that the lighter ones are deflected more, and that the charge also affects. The positive charges are deflected more than those. The more positive charges are deflected more. So these are both variables that you need to know. However, they tend to focus on the mass. There's a mass-charge ratio. This is something that would be pretty rare for them to ask, but we might as well cover it. If you have a mass of 28 and a charge of +1, your mass ratio is 28. You'd have the same mass ratio with a mass of 56 and a +2 charge. When you're given the mass spec data, it can be given in terms of percents or those relative masses, and we worked several of these in class. If you have relative masses, the highest peak is assigned 100, so you basically have 123 here, so your percent of the smaller isotope is 23 out of 123. It really makes no difference at all. It's that you understand this is finding the average mass from isotopes, and it's a weighted average. They could give you something fairly confusing. This is a mass spec of bromine, and when you have diatomic elements, obviously each isotope form, if you've got diatomic elements and 2 isotopic forms of bromine, you could have 2 different combinations of those isotopes. So I like this question as an advanced mass spec, and we did talk about this one in class. To the left, you've got your monoatomic bromine 79 and 81, and to the right, your 3 different types of Br 79 and 81, and 79 and 79, and 81 and 81, and so on. These are the equations provided on the exam. You could be expected to solve for any of them, so it won't be multiple choice most likely. Would be a free response. You did this in the 11th grade. You did it most recently with the spectrum tube, which you very well might remember. The more useful equation at the bottom, lambda is equal to hc over E, I don't think is provided on the exam, but it can be manipulated from the others. PES, photoelectron spectroscopy. This is measuring the energy of electrons in their orbitals. The idea of this is based on Coulomb's law, where you've got the electrons attracted to the nucleus to differing degrees depending on the nuclear charge. So Q1, your charges there are your nucleus attracting your outer electrons, and then the distance from the nucleus. So Coulomb's law works for electrons and atoms as well as ionic bonding and covalent bonding. So just to remind you of Coulomb's law, you can pause on this slide if you want to review more. Your photoelectron spectroscopy is not much in detail that you need to know at all. You expose your sample to high energy, usually X-rays, knock the electrons out. They go through some analyzer that measures the kinetic energy. If you remember, did that Pogel with the soccer ball in the ditch idea. What we learned from PES data, though, is pretty important. The Bohr model gives us energy levels, and the PES data gives us those sublevels. The P's, the fact that at the second energy level you have an S and a P. Don't forget that the way that the graphs are set up, the energy to the left is a more tightly bound electron. So putting that little proton to the left there kind of reminds you of the nuclear charge. That probably won't be provided that way. But you've got electrons closer to the nucleus, those further, the higher the peak, the more electrons, and so on. So comparing two atoms, very probable question. Hydrogen, helium, peak of hydrogen, smaller, 1 electron. Helium, larger, 2 electrons. Helium, closer, higher binding energy, closer to the left, 2 protons, and so on. So there's a lot of little questions they can ask. Could be multiple choice, which is all it's been up till now, but probably a free response coming your way. And we'll work a few more of these, but you have done a fair number. You just have to review. So again, your oxygen, you should certainly be able to take a PES and come up with an electron configuration and discuss, again, based on the energy of those electrons. Remember, the binding energy is greater to the left. So obviously your 1s electrons are held tighter, and your 4 electrons in the 2p are held more loosely. But the binding energy is different than the potential energy. So the electrons in the 2p have higher potential energy because they are further from the nucleus, while the electrons in the 1s have higher binding energy, lower potential energy. Rotational spectroscopy, again, I mentioned earlier, is simply based on microwave energy, and you rotate molecules, polar molecules primarily, and primarily water in your microwave oven is rotated with these microwave energies. I don't really think they would ever ask you much about rotation. I just want to make sure you know the difference between the different types. So we've looked in more detail at the PES, the mass spec, and the spectrophotometry or colorimetry. So the rotational spectroscopy, that amount of energy just rotates molecules. And then I think they would be a little more likely to give you a little more in-depth question on the infrared. Molecules absorb frequencies characteristic of their structure. They have different resonant structures, so you get that bond to vibrate back and forth. You did a very short COBAL on this, and we never actually went over it. We kind of had to put it aside. I don't think you're ever going to have to read and interpret unless they gave you specific information, such as this kind of stretching of the bond is this structure, and then maybe you would draw a structure or something along those lines. But you simply need to know what information you can get for infrared, and that can give you, of course, pretty detailed structural information. Your atomic orbitals, okay, you no longer need to know your L, M, L, and MS quantum numbers. You do need to know your principal quantum number. N means energy level, 1, 2, 3, 4, N equals 1, and then, of course, sublevels, SPDF, orbitals. You need to know how many there are, and, of course, a spin number. Be able to write electron configurations and interpret from them. Periodic table is provided for you, so any shorthand electron configuration should be easy to figure out, but remember they may have you write longhand, so read carefully. From that, they'll probably have you interpret ionization energy, nuclear charge, radius, and so on. Para and diamagnetic, spend maybe 2 minutes reviewing them. It's not going to be a big deal, but you should be able to say if electrons are paired or unpaired. Hopefully they won't ask the question specific, but they have before. Isoelectronic, kind of a big deal. Make sure that you know an isoelectronic series of the anions, including the noble gas and the cations, that all have the same number of electrons, different protons. A lot of good questions could come from that. Atomic radius, ionization energy. When you have the same electron configuration but different protons, use some common sense. The more protons, the tighter the electrons would be held, the more difficult to remove them, and so on. Radius, as you go down, your primary factor is an entirely different energy level, okay? And you get shielding as well. Going across, you really want to focus on increase in nuclear charge for all of these trends. Coulomb's law, Coulomb's law, Coulomb's law. Again, charge, opposite charges attract. The further away they are, the weaker the attraction. So anytime you can relate to Coulomb's law to discuss these, you're in good shape. Do not say they want to become a noble gas. They are stable, blah, blah. Don't say that. You either have high attraction, low attraction, you're further away from the nucleus, closer, and so on. Effective nuclear charge, again, is as you move across the periodic table and you're adding those electrons in the same energy level with no additional shielding, you have a greater effective nuclear charge. Ionization energy, energy to remove an electron, depends on how tightly the electron is held. If you're answering questions, be very specific about what energy level it is. Talk about first ionization energy. That's usually all they're asking about. Second ionization energy, excuse me, would take more energy because you're now removing an electron from a positively charged ion that is holding the electron tighter. Successive ionization energies always increase. By their increasing, you can tell exactly when you are making that jump into the core electrons. So for aluminum, each ionization energy goes up, but when you make that large jump, you can tell that you're moving into those core electrons. You've jumped down one entire energy level, so your more stable charge would be a +3 for this. And from that, you could probably identify an element. So when you're moving across, I don't think there's anything new here. Electrons are further away as you go down. Let's move on. Electron affinity, we don't focus on it much, but obviously your nonmetals want to pull electrons or have the ability to pull electrons into their orbitals. Adding an electron, this is the equation for electron affinity, often releases energy. It does not always release energy. All of your halogens have high electron affinities and high ionization. They don't want to, they're very difficult to lose electrons because they're holding them so tightly, but very easy to gain them. Your chemical bonding. Make sure you can differentiate all of your types of bonding. Ionic bonding, again, to differentiate between ionic compounds, Coulomb's law, charge over radius of the ions. So now you're using Coulomb's law with bonding instead of just atomic structure. Electronegativity is a measure of the ability of an atom to attract electrons to itself when it's in a compound. So the differences in electronegativity determine everything about bonding, everything. That is why you have an ionic bond when you have low electronegativity and high electronegativity, such as metals and nonmetals. You get a more full transfer of electrons, and then everything else is a more equal sharing or an unequal sharing. That creates your polar bonds and your nonpolar covalent bonds. Your bond stability, that overlap of the orbitals occurs at a minimal distance. with a minimal energy. If you try to force them closer together, you can see the energy goes up. So there's an optimum internuclear distance. Both nuclei are trying to attract electrons towards them, and this is the optimal overlap of those orbitals. Your bond polarity, or a dipole in a bond, is again due to differences in electronegativity, so you might have to indicate partial positive and negative charges. There are lots of ways to do that, with the arrow, with the positive partial charge, but this is just polarity of a bond. Polarity of a bond is not the same as polarity of a molecule, but bond polarity is an important concept, and you have stronger bond polarity when you have a greater difference in electronegativity. Lewis dot rules, you can review them, you can stop and review them. I'm not going to read them out. You need to be able to draw Lewis dot structures in your sleep. You need to know those elements that can break the octet rule by exceeding it, and boron tends to be electron deficient, and why? Based on those d orbitals they can exceed. Bond length, again, depends on the radius of the two atoms that are going to be bonded, so your bond length would depend on radius differences, and from that bond length, you get bond strength. So the closer the atoms are to each other, the shorter the bond length and the stronger the strength. So that should make perfect sense. Again, can't say it enough, Coulomb's law. Your multiple bonds are shorter and stronger. You have a greater electron density. You could be asked to calculate a thermodynamic function with bond energy. Not a hard thing to do. You have to remember it's bonds broken minus bonds formed. So here's an example. You'll be given bond energies. Sum them up. Don't forget to multiply by the coefficient. Watch your math. Show some work. If it takes more energy to break your bonds than you get back when you make them, then you're going to be, well, let me say that again. If it takes more energy to break the bonds than you get back when you make them, you're going to be endothermic. And if you get back more energy when you make those bonds than it took to break them, you're going to be exothermic. Bond order also tells you something about bond strength. Really, all you're doing with bond order is figuring out how many multiple bonds you have. If they're all single, you have a bond order of 1. If you have double, it's 2, and triple, 3. So the higher your bond order, the stronger your strength, and the shorter your bond. It's sometimes easy to get confused with that. If you have a more complicated molecule where you have a combination, you're going to be adding up all of the bonds divided by the number of bonding groups. So in this case, you would count the double bond, okay, each one of them. So this is unlike Lewis dot when you're coming up with the geometry. So you count 1, 2, 3, 4 bonds divided by 3 bonding sites, or 3 things attached to the central atom, gives you an average bond order of 1.33. Common sense tells you you've got 1 double bond out of 4 total bonds, so you've got your 1.33 average bond, which shows you that it's stronger than a single, but not as strong as a double. So the stronger bond has a higher bond order and a shorter bond length. Really good free response. And they could also add into here the idea of resonance. Remember, even though right in front of you it looks like you have a double and 2 singles, in reality there would be 1 bond type, and that's what bond order is telling you. 1 bond type with an average of 1.33. You don't have a bond flipping back and forth. You have an average bond. I threw this in here just to remind you every once in a while you can get an odd number of electrons in some advanced molecules. You would put that odd electron on the central atom, and most likely it would be nitrogen. Resonance, one bond length. To show resonance structures, draw them both with a little double arrow between them. Again, nice resonance structures showing the 1.33 bond order, indicating one type of bond. To determine the preferential resonance structure, if there is one. Now, in the three we just looked at, they're all equivalent, but sometimes you have one that's better than the other. You use the idea of formal charge and try to get atoms with formal charges as close to zero to give you the dominant form. Formal charge, add up the valence electrons for that element, subtract half of the bonding and all of the lone, and that will be its formal charge. So we did carbon dioxide in class. We looked at several different structures, the triple, single, and the two double, and came up with a better formal charge for the two double bonds. Molecular geometry. VSEPR is telling you molecules adopt the shape that minimizes electron pair repulsion, so atoms are attracted to the central atom, repelled from each other to varying degrees. That gives them their molecular geometry. You've got to know your shapes. You've got to know your polarities. You've got to know bond angle effect of lone pairs. You've got to be able to break the octet rule and understand the geometries that are going to come from that. Once you have drawn a molecule's Lewis dot, stated its geometry, you'll probably have to talk about its polarity. Remember, you can have polar bonds, but if the dipoles cancel, you have nonpolar molecule overall. So look for the symmetry, lone pairs that aren't canceling. State your polarity very clearly. So, you got nonpolar molecules. If you have polar bonds, the molecule is symmetric. The dipoles cancel. If it's not symmetric, the dipoles don't cancel. Knowing polarity is important because you got to come up with your intermolecular forces based on polarity. Hybridization is as simple. We took a while to get it straight in our head, and it still may not be in there, but it's a blending of those orbitals that actually give you that geometry. In order to have a tetrahedral, you have to have 4 equivalent bonds, and an S and 3 Ps, they don't hybridize, are not going to give you 4 equivalent bonds. They're not going to be pointing in the directions you want. So your sp3 hybridization has no multiple bonds, gives you a tetrahedral. It's the simplest of all. sp3 hybridization is anything based off the tetrahedral. Tetrahedral, trigonal, pyramidal, and bent. Anytime you have 4 effective pairs. 109-degree bond angle. If you have lone pairs, that bond angle gets smaller. Your sp2 hybridization blends 2 of your P's and an S to give you 3 equivalent bonds. This will give you 120-degree bond angles between them, and that's the trigonal planar. So you've got sp2 hybridization. You also have an unhybridized P that allows for a multiple bond. is a good example of sp2 hybridization. sp hybridization gives you a linear structure. You're blending a P and an S for 180-degree bond angle. Linear, triple bonds, double bonds. So you simply need to be able to state the hybridization around whatever central atom they're pointing to. Once you have all of your molecular structure polarity down, you're going to have to deal with your intermolecular forces. Just covered this with the juniors. They did great on the test, so pretty sure you will nail this. Your intermolecular forces are based on your intramolecular forces. Please make sure you know the difference between them. When you're talking about intermolecular forces, you're just talking about phase changes, melting points, boiling points, freezing, so on. Your strong forces between atoms and your weak forces between molecules. Crucial that you don't get these confused. Your ionic solids, you know the properties of those. Ion-ion interactions. Again, Coulomb's law. Dipole-dipole, any polar molecule. Permanent dipoles, positive to negative ends. Within dipole-dipole, you do have the ability to have a particularly strong force called hydrogen bonding. You've got to have hydrogen covalently bonded to F, O, or N. That's it. Covalently bonded. That's not the hydrogen bond. Once you have that covalent bond, then you have a strong intermolecular force attraction between the hydrogen on one and the oxygen or nitrogen, fluorine of the other. Your London dispersion forces are in every type of bonding, ionic, dipole-dipole, hydrogen bonding, but when you have nonpolar molecules, they're the only forces of attraction. You have this instantaneous and induced dipole. It's temporary, it's weak, but the larger your molecule, the more force you can have that's fairly significant. Remember, in nonpolar, these are the only. But if you were looking at two dipole-dipole and you decided, okay, two polar molecules, both dipole-dipole, what am I going to do now to differentiate? You've got to go down to your LDF forces. When you discuss stronger London dispersion forces, you can say bigger molecules, but you better not say more mass. Bigger molecules have more electrons, more chances for polarizability. Don't say mass. You can find mass. Bigger, again, does mean more mass, but you have to say more electrons. Your strength of intermolecular forces overlap, and that's part of what they will be asking you about. They'll be trying to not trick you, but make sure you can support why something has a stronger force than something else. Your metallic solids, electron C model, not much to say there. Make sure that you understand how this affects malleability and ductility. A pretty visual model. The alloy notes, I'm not going to read through these. I'm going to let you stop and read if you need to, but you definitely need to know a little bit about alloys. Probably not nearly as much as the notes I have here. But know the difference between interstitial and substitutional. You saw that on a multiple choice. Make sure that you know alloys are created to change the properties of metals, to change their strength. Also can change their hardness, ductility, conductivity. Semiconductors, again, something you might need to know something about. It's certainly been added to the exam. I've not seen a question on it yet. Now, it might have been on the multiple choice. We don't get those released. But we've gone through these, so I'm just going to go through the notes and mention a few things, and if you want to stop and review, that's fine. Make sure you know conductors, insulators, semiconductors, the best conductors. You want to have one electron in your outer shell to be a really good conductor, and it's that valence electron that's stripped off and allows for current flow. Good insulators, again, have a high resistance and do not allow electrons. The electrons are held tightly. Semiconductors have an ability to act like good conductors and good insulators and anything in between. Silicon is as one of the best semiconductors, as well as germanium and carbon. The main characteristic of a semiconductor, those 4 valence electrons. They bond with each other to form a crystal lattice. They share their outer electrons. A pure semiconductor, okay, is not going to be much of a conductor. It's a pretty good insulator. To make the semiconductor conduct better, you add an impurity this process is called doping. So if you have 5 valence electrons like arsenic, 4 of them bond like the crystal lattice, and you stick that little impurity in there with the 5 valence electrons, and now that electron is free to move, just like the metals with 1 valence electron. So focus 4 valence electrons with silicon, pretty good insulator, add an impurity with 5 valence electrons, get that one single one, it's free to move. You can also dope with 3 valence electrons. So now, instead of an extra electron, you have a little hole there. That hole actually acts like a positive charge that pulls electrons into it and also supports the current flow. That's when they use boron. So you have an N-type conductor, N for negative extra electron. The P-type, which is positive, which is the boron, which is the hole, and the positive charge pulls the electrons towards it. Pure silicon, N-type extra electron. P-type, positive hole, where electrons can move in. Then you've got carbon. The forms of carbon that you need to focus on are graphite and diamond, and primarily diamond, because they want you to know network covalent solids. These are huge macromolecules. The big idea here is that their intramolecular forces are their intermolecular forces. So you've got carbon bonded to carbon with these directional covalent bonds. This makes it an insulator with extremely strong forces. sp3 hybridized, tetrahedral, strong sigma bonds. Quartz has the same basic structure, silicon dioxide. Again, electrons are not free to move. They are not delocalized. Delocalized electrons are electrons that are free to move, like in metals. Graphite is not macromolecule. It's not network covalent solid. It does have interesting bonding. sp2 hybridized. Electrons are free to move through those pi bonds. It's a conductor. It is soft. So now your strength of intermolecular forces, your network covalent solids are way out there. There's hardly any overlap there. You're not going to get any overlap. You're not going to get hydrogen bonding being stronger than ionic. So network solids and ionic are pretty high to the left. Other things can overlap. Energy of making solutions is also based on your intermolecular forces. You've got to break apart your solvent, break apart your solute, and then they've got to attract each other. Some good questions that I've seen on this. If you have a polar solvent, you've got a large delta H1, like water. It takes a lot to break those hydrogen bonds. If you have an ionic solid, it takes a lot to break the ions from each other. So you've put a lot of energy into expanding the solute and solvent, but get a lot of energy back when they form because they are attracted to each other. Anything that's polar-polar or non-polar is going to have that strong attraction, and that will drive the reaction forward, as well as the increase in entropy. So like dissolves like is not something you can say. Don't say that. Don't say that. But you can talk about structures that are similar. You can talk about ability to hydrogen bond with each other. You can talk about inducing a polarity. So water and this is two methanol molecules. Methanol hydrogen bonds with itself. It also hydrogen bonds with water, so it's quite soluble. Ammonia and water, hydrogen bond. Water has the ability to induce polarity in some fairly small nonpolar molecules like oxygen, carbon dioxide. It can even induce a small polarity in large molecules like iodine, but it does take a bit of work. So if they tell you something is sparingly soluble in water, then obviously water induced a dipole. So if you have a nonpolar substance that somehow becomes soluble, water had to induce a polarity. Temperature increases the rate of solubility, but it doesn't necessarily make something more soluble. You actually have to have more data to determine that. Your organic, you need to know very little, but it's very helpful to know your hydrocarbons are always nonpolar. Okay. Any hydrocarbon, whether it's saturated or unsaturated, if it contains only carbon and hydrogen, it is not possible for it to be polar. You can have more or less LDFs, but it's still not polar. Some of the naming might help you with the structure. If you happen to know butane is 4 carbons, but mostly you're just simply going to be shown organic compounds and you don't want to freak out when you see them. Isomers, while they don't expect you to know organic, they might ask you to draw an isomer. So you simply want to make sure that you can figure out how to move those carbons around each other so that you have a different structure. Alcohols always end in OH, methanol, ethanol, or they may say alcohol, and they've got that OH group, and they are able to hydrogen bond. Depending on how large the nonpolar part of the molecule is, though, they may not be water soluble. So methanol is water soluble. Butanol is not, even though it can hydrogen bond on that end. It's got much too large a nonpolar section of the molecule that water cannot interact with. Your organic acids are weak acids, all of them. So if you see that COOH, they're also able to hydrogen bond. They're quite water soluble. And then, of course, you have your amines, which are your weak bases. You have to recognize those. They also can hydrogen bond with water and with themselves. So this covers a lot of chapters, I think 7, 8, 9, 10, and 11.